So in this recording, we're going to talk about what do you mean by returns to scale and how do you calculate returns to scale with few examples and what is the meaning of decreasing, increasing and constant returns to scale, right? So the question is that how output is going to respond if inputs are going to change, if all inputs are going to change together, right? So that's the question. And for this, we need to answer using returns to scale. So let me just write a few points. That is how output responds to an increase in all inputs together. How an output respond to an increase in all inputs together. So Adam Smith, he also tried to look at this question. He said this that if you double all the inputs, then what can happen? He said this that yes, if you double all the inputs, one thing which can happen is whether it will happen or not that nobody knows. That's an empirical question. But one thing which can happen is that there could be a greater division of labor, right? So with greater division of labor, it will bring about efficiency. When efficiency will increase, there is a possibility that yes, your output can even more than double. So although you have just doubled the input, but your output can more than double, right? So one possibility is doubling all inputs permits a greater division of labor, right? So efficiency might increase. Efficiency might increase. Production may more than double. Production may more than double. So you have doubled the inputs, but your output can more than double. Then there is also another possibility which can also arise, that when you double all the inputs, managers would have to sort of what do you call supervise more amount of inputs. So the managerial efficiency might fall, which might lead to a lesser increase in output. So it is difficult to manage a very large scale or a large size firm because you have just doubled all the inputs. It becomes increasingly difficult to manage such a firm. So the production may not increase uh, by that much with which you would have thought. For example, you've doubled the inputs, your output might not even double, it might less than double. So doubling all inputs may also entail some loss in efficiency. Some loss in efficiency because of managerial overseeing. because of managerial overseeing, which may become increasingly difficult to manage a large size firm, right? Because of managerial overseeing becoming more difficult given the large scale of the firm. Given the large scale of the firm. So this is the case of, this could be decreasing returns to scale. So you have double the inputs, but your output may less than double. So the first case could have been of increasing returns to scale. That is, you double the input, your production may more than double, right? Now, which one will happen? Nobody knows that, right? I mean, it is an empirical question. That so the other thing is that they could also be a constant returns to scale. So constant returns to scale would be uh, the case, for example, that is also a feasible case for few things. For example, if the firm is operating many identical plants, right, and it can just vary the number of the plants. So completely identical plant, every plant will have same amount of inputs, it is producing the same amount of output. So it can increase or decrease the input, and that will result in increasing and decreasing the output in the similar manner, right? So the firm can actually double the output by doubling the number of plant it is operating. That is also one of the case. Uh, so if the firm operates many identical plants, it may increase or decrease the production simply by varying the number of them in the current operation. Hmm? In the current operation. So they can just increase or decrease. For example, in case if they just double the amount of the plants which they are operating, they're identical plants, everything is same, right? So they will be able to double the output. So that's a case of your constant returns to scale. Uh, so possibilities, all of these are different possibilities. Now, how do you technically define returns to scale? So that's the meaning. Let us look at a few technical definitions. So the production function is given by Q is equal to f of KL, right? And if all inputs and if all inputs are multiplied by the same positive constant, lambda greater than 1, then we classify returns to scale of the production function in the following way. Beta, you have the production function q is equal to f of kl, right? You increase k and l both by lambda. Hmm? So this is going to give you, okay, I'll write it with a different ink. This is going to give you the output due to the doubling of inputs. This thing. That's what it is. So instead of using just k and l, you're using uh, 2k and 2l. So when I write double, I mean lambda is double, right? So it is, you're just doubling it, right? Okay. And this was your initial output. Hmm? If you multiply the initial output by lambda, by the factor with which you are increasing, so let's say you're doubling inputs, and if you just multiply the initial output by lambda, this is what you're going to get, lambda into f of k. So if the output which you're going to get by doubling of the inputs is more than double of the output, this is the case of increasing returns to scale, right? So the output which you get by doubling of the inputs is more than double of the output. So I'm writing double, I mean that lambda is doubled here. So this lambda f of kl is doubling of the output. Doubling of the output. You with me? So the output which you're going to get by doubling of the inputs, if it is more than doubling of the output, right? Doubling of the initial output, this is what is called increase in returns to scale. So you double the inputs, the output which you're going to get is more than double the output, right? So this is what increasing returns to scale is. Right? This is what increasing returns to scale is. Hmm? Increasing returns to scale, right? So a simple example would have been, for example, f of kl is equal to k into l. That's it. So you increase k and l by lambda. So instead of writing your k, you write lambda k. Instead of writing l, you write lambda l. And what you get is lambda square kl. So because this lambda is completely factored out, is this is the homogeneous function, and the degree with which it is factored out is the degree of homogeneity. So when it is greater than 1, so this degree of homogeneity, so for the homogeneous function, it is very easy to find out returns to scale. I'll give you one example in which the function is not homogeneous, and then how do you find out returns to scale? Degree of homogeneity. Guys, I've made the video on homothetic and homogeneous functions earlier as well. So if you have a problem understanding this, you have to go back to that video. So degree of homogeneity is 2. So if it is what do you call, greater than 1, so this is the case of increase in returns to scale. So if the degree of homogeneity would have been, I mean, in this case, let's say if it was alpha and beta, so this would have been alpha plus beta. So if alpha plus beta is greater than 1, means, I mean, you are this is the case of increasing returns to scale. So you have increased the inputs by lambda, but your output has increased by more than lambda, right? So this is one thing. Second thing is, f of lambda k lambda l. So the output which you get by doubling of the inputs, if it is less than double of the output, right? If it is less than double of the initial output, this is the case of decreasing returns to scale. If it is less than double of the output, this is the case of decreasing returns to scale. So, for example, now here I'll give you one example of a non-homogeneous function. So let's say you have the function f of kl is equal to lambda k plus n, like this. So what you do, you increase knl by lambda. So you like this. So lambda is not completely factored up. So just depending on that homogeneous function definition, you cannot answer returns to scale. So you'll have to use logic only. So can I write this as lambda k plus lambda l? This is what I'm going to get. Root of lambda into root of k plus lambda l. This is what I'm going to get. Now this is less than lambda is there, no beta. So just think about it. This is what f of lambda k lambda l is. This is what lambda f of kl is. Huh? So the increase in output by doubling of the inputs is less than double of the output. So this is the case of decreasing returns to scale. So it is not that you need a homogeneous function only in order to tell whether what is the returns to scale. No, that's not necessary. Then you have constant returns to scale. So you double the inputs, and the output which you get is just the output which you get from lambda k lambda l is just double of the output. That is what CRS is. That is what CRS is. Uh, so, say for example, you have the question like this. I'll give you one example. You have f of kl is equal to ak plus bl. You have like this. And you increase both knl by lambda. So what happens is, look at this guy, lambda ak plus bl, right? So f of lambda kl is nothing but equal to lambda f of kl. So you double the inputs, the output which you get from doubling of the inputs is equal to double of the output, right? Is equal to the doubling of the output. So this is CRS case. Acha, you tell me one thing. This is homogeneous of what? Degree 1? Huh? This is homogeneous of degree 1? Okay. If I want to write the MPK for this, that is what? Del F by del k. In this case, it is A. Hmm. Now, this is homogeneous of degree 0. That's what it is now. This MPK is homogeneous of degree 0. That doesn't matter because, so you can write your MPK as a function of K and L, but this is just A. You know? That means you increase lambda K and lambda L. You increase K and L by lambda, but this is just A. There is nothing here. There is no K and L here. It doesn't matter. So it is just, I mean, as if you are writing it like this. Lambda to the power 0 into 1. है ना? So lambda to the power 0 means degree of homogeneous of degree 1. So the reason I'm telling you this is this. If you have a homogeneous function, its first order partial, if you have a homogeneous function of degree k, its first order partial derivative is homogeneous of degree k minus 1. That is there. Okay. So if you have a production function which is homogeneous of degree 1, so its first order partial derivative, which is the marginal product of capital or marginal product of labor, is homogeneous of degree k minus 1. You with me? So let me just write that. If a function is homogeneous of degree k, its first order derivative, first order partial derivative, is homogeneous of degree k minus 1. So in this case, MPK is the first order derivative of the production function. This production function was homogeneous of degree 1 and its first order partial derivative with respect to k is homogeneous of degree 0. Keep this thing in mind, right? So if the production function is linearly homogeneous, marginal products would be homogeneous of degree 0. Linearly homogeneous means degree of homogeneity 1. If production function is homogeneous of degree 1, its marginal products are homogeneous of degree 0. If production function exhibits CRS, its marginal products are homogeneous of degree 0, right? So if you had a question, you had the case like this where you have uh, f of lambda k, lambda L is equal to lambda f of kl, that is just homogeneous of degree 1, it is a CRS function. uh, then you can write mpk as what? Del f kl by del k. You could have also written that as, it doesn't matter now, right? Hmm. So del f. Acha, I can also say, let's say lambda is equal to 1 by L. Let us say. So I can write this as, if lambda is 1 by L, so I can write this as k by L, comma 1. Similarly, MPL is del f KL by del L. You increase both lambda K lambda L. You increase both K and L by lambda. Just writing this in terms of L, that is lambda is equal to 1 by L. Mhm. By del, right? So this MPK is actually dependent upon the ratio of inputs which you are using, K by L. In case of CRS production function, CRS means linearly homogeneous production function, homogeneous of degree 1. Let's take a one more example. So you have f of KL is min of AKBL, right? So in place of K, I can write lambda K. In place of L, I can write lambda L. I can take lambda common. So this lambda is completely factored out, degree of homogeneity 1. And this min of AKBL is nothing but f of KL. है beta? So f of KL is nothing but equal to lambda of f of KL. So this is nothing but CRS production function. This is nothing but CRS production function. L to the power beta, Cobb-Douglas production function. So in place of K, you can write lambda K. In place of L, you can write lambda L. You can take lambda common. Right, beta? Now it all depends whether alpha plus beta is greater than 1, equal to 1, or this thing. So in case if alpha plus beta is equal to 1, then this is a CRS case. Why? Because f of lambda KL would be equal to lambda of f of KL. So I can also write it like this. Just wait. Hmm? So if f of lambda k lambda L is equal to lambda f to the power alpha plus beta f of KL. If alpha plus beta is equal to 1, so this is equal to just lambda f of KL. That is CRS, right? So it all depends upon this alpha plus beta. Alpha plus beta greater than 1, this is IRS. Alpha plus beta less than 1, this is DRS, right? Okay, so this is what I wanted to do in returns to scale. Thank you, beta.